All right, this is section 5.1, solving systems of linear equations by graphing. So far, we have learned how to solve systems of equations using substitution, and then we learned how to use elimination, which both have their advantages and disadvantages. Some problems are set up for substitution, some are set up for elimination, and some are set up for graphing. Graphing is the third and final way that we're going to learn how to use or how to solve system of equations. So this first problem I put on here was actually copied from your graphing review worksheet that we did before you guys left for Christmas break. You may remember the Happy Paws and the Wolf Watchers problem, where you had to solve each of these, and it says the cost is same at how many hours down here at the bottom. Well, what we had to do is we had to set up an equation C for cost, so for Happy Paws, the cost was equal to $3 per hour plus a $5 initial fee. And for Wolf Watchers, the cost was equal to $2 per hour plus an $8 initial fee. And what we could do is what we actually did is we graphed each of these. You may remember we graphed the Happy Paws, which had a y-intercept of 5, and it was rising 3, running 1, and rising another 3, running another 1. I think I'm counting. No, that was not the right spot. Let's go over 1. There we go. And we could draw a line once we get this down. See, they're pointing right there, and another one. I think that's probably going to be enough. So we draw the line that goes through those points. So there's the cost flow of Happy Paws, and then we've got Wolf Watchers, which I'll do in blue, and its y-intercept was 8, and its slope was rise 2, run 1, rise 2, run 1, rise 2, run another one, and you can see that its intersection was right here. And so that for us was 3 hours. At 3 hours, we could see the cost was the same. And if it's after 3 hours, then Wolf Watchers is going to be less expensive. And if it's before 3 hours, then Happy Paws is going to be less expensive. But what we did when we solved this problem, I don't think we knew it, is we were solving a system of linear equations because we have two equations. We've got a Happy Paws equation, and we've got a Wolf Watchers equation. So that's a system of linear equations, and we just found the intersection. Not only can we tell that it's at 3 hours that the cost is the same, but that cost, if we go over here, that cost is going to be $14. So now we have a coordinate point of at 3 hours. Whoops, go back and write this. At 3 hours, our cost is $14, and we could label. So that is what we're doing today. We're solving system of linear equations by graphing, and it's going to be really helpful if our system is written in slope-intercept form, obviously, because that's how we graph equations. You may also remember this question from your 5.3 elimination homework, where you were supposed to write the equations of the blue airplane and the red airplane. And we did that. We wrote the blue one and we wrote the red equation in slope-intercept form. Did you notice that it didn't ask you to solve? It just gave you these boxes down here where you just had to write the equations, but it didn't ask you to solve. Well, the reason we didn't have to solve is because we knew exactly where these planes were going to intersect, right here at the airport. So if I were to draw the blue line that goes towards the airport, and if I were to draw the red line that goes towards the airport, their intersection would have been at the airport because that's where they were both landing, and the coordinate for the airport was 6, 12. That would have been our answer, but you know, they already gave it to us, so we didn't have to write it. So all we need to do if we're solving by graphing is we just need to find out what that coordinate point is when these lines intersect. So here are your instructions, your steps for solving by graphing. First of all, we want to make sure both equations are written in slope-intercept form. That's very important. Remember, that's y equals mx plus b. So that's how we want to write these so we can graph them. Then we're going to graph each line. We're going to find out where they intersect, and we're going to write it as an ordered pair. Remember, if I was using substitution, I would substitute y in for the, mx plus b in for the other y. So if I was using substitution, I would do mx plus b. I'm replacing this with y equals mx plus b. And what we're doing when we find out where they equal graphically, so algebraically, we put an equal sign between them, but graphically, we just see where they intersect. In graphing, if two lines intersect, that's where they're equal to each other. So that's visually what this is going to look like. All right, so let's look at the first two problems. Both of them in part A are written in slope-intercept form. So we've got a slope of 2 and a y-intercept of 5. So rise 2, run 1. I can also go the other direction, and I can put dots through here. I'm not using notability, so I don't have the ability to make a super straight line. So I'm going to do my best here of saying that's where the red line is, not very straight. And then, so I'll make that the red one, and I'll make this one blue so we can see it better. Whoops, always click on the highlighter. So I'll make that one blue, and that one has a y-intercept of -1, and it has a slope of down 4 over 1. So up 4, left 1, I can already see where the intersection is going to be, and I can draw my line right like that, and my intersection is going to be right here, and that is the coordinate point. So remember, I have to answer it. I can't just intersect them and say there it is. I have to answer the question. That's at -1, 3. Remember, we put the x first. So this is why we've been writing our answers as coordinate points, because graphically the coordinate point is the answer to where they intersect. So using substitution or using elimination doesn't matter. You've been finding this whole time where they intersect. All right, so the second one, example B, we've got a y-intercept. I'll do green for this one. We've got a y-intercept of 3 and a slope of -x. So down 1 over 1 means I'm going to be going all the way through my graph, right like that. Down 1 over 1. Then I can also go up 1, and I can go to the left 1 through my graph like that. And then for the next one, y equals -1, that doesn't have a slope, right? There's no mx, so that means the m must have been 0. So this is going to be a horizontal line, and it's going to cross the y-axis at -1. So it's actually this line right here. And now I can see where my intersection is, right there, and that's the coordinate point for -1. So now I've answered my question. Where have they intersected? All right, so for the next one, we've got y equals x. So that means the slope is 1, and the y-intercept must be 0, right? So it's going to go through the origin, and the slope is rise 1, run 1. So I'm just going to keep going up, 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 up 1 over 1, and same in this direction. Okay. And then my second line, which I'll do purple, my second line has a y-intercept of 3 and a slope of rise 1, run 4. And you can see that it's going to intersect right there, and the coordinate point for that is 4, 4. So that's my answer. And then for the next one, we've got, I'll do this one red, -5 for our y-intercept, and it's going down 1 over 1. And that means I'm going all the way up here, up 1 and to the left 1, takes me all the way in that direction. Again, I don't have the ability to do a straight line, unfortunately. Let's erase this purple dot here, if I can. Okay, it's not letting me erase it. Okay, so then for the second line, I'll do that in blue, and that's going to put me right here at 1 on the y-axis, and then my slope is rise 3, run 1. Oh, I guess that's exactly where I want to be. And I want to go down 3 over 1 as well, down 3 over 1, and we run into a little bit of an issue here. The issue being that these lines intersect, but they don't intersect at a spot that's really easy to tell. I mean, that looks like it's halfway between -1 and -2 for the x, so maybe -1.5, and it looks like it's halfway between -3 and -4 for the y, so maybe -3.5, but we're not really sure because it doesn't have an exact intersection point at one of these nice little blue lines. So we're running into a little bit of an issue with graphing. So one disadvantage to graphing a system of linear equations is that it's not always easy to find that exact intersection. So if I wanted to be sure, how could we tell? How could we tell what the solution is? And the answer is well, you've got other ways, right? We've learned two other ways. You could use substitution to tell. So if we want to plug 3x plus 1 in for y, 3x plus 1 equals negative x minus 5. Move your x's over to one side by adding x to each side. 4x. And then if we subtract 1 and move that over to the other side, that gives us negative 6. And then we get x equals negative 6/4, which is the same as negative 3/2, which is the same as negative 1.5, which we said that's what we thought x was up here, right? Negative 1.5. And then if we solve that for y, we could plug it in. I'm going to plug it in right, oops, let me change that. I'm going to plug it in right here. So negative 1.5 is 1.5. So y equals 1.5 minus 5. And 1.5 minus 5 is negative 3.5. And that's what we estimated the y to be up here. So again, I was correct, but you could use substitution if you're not sure exactly where they intersect. That is one disadvantage to graphing, is that sometimes they don't graph it, they don't meet at perfect spots. And if we use algebra, we don't mind, but using graphing, it's sometimes hard to tell. All right, so sometimes we have to convert our equations into slope-intercept form. We can see the top equation already is, and then for the bottom equation here, if we just subtract x from both sides, that's going to give us y equals negative x. Remember that x needs to be written first because it's the part of the slope, right? The x mx plus b. And then we can move this to slope-intercept form, and then we can graph it. So we've got negative 7 for our y-intercept all the way down here, and then it goes down 4 over 1 to the right, but we can't go down any farther. So instead, we're going to flip this around, and we're going to go up 4 and 1 to the left. That'll be the same. And then I can put a point there, up 4, 1 to the left. Okay, make sure you are graphing these lines and not just putting dots through them. And then for our purple line, we've got a y-intercept of 2 and a slope of negative 1. So that's down 1 over 1. So that's going to go in this direction. And then make sure I line this up perfectly. Put my dots there. You can see the intersection is going to be right there. And that is the point, negative 3 for the x and 5 for the y. Now, for this second one, we need to move I'll write it down here. We need to move the x over, but that's going to give us negative y equals negative x plus 5. So then I have to times everything by negative 1, both sides. Remember, we know this from elimination. You have to do every single number has to get times by negative 1. So there I can graph negative 5 for my y-intercept, and the slope is rise 1, run 1. So all the way up to here and then down here. And then for my other line, we've got to do quite a bit of work. I'll write it down here. So first thing we would do is we would move the negative 6x to the other side, write it as a positive 6x minus 2. And then we're going to divide everything by 2. Y equals 3x minus 1. Everything gets divided by 2. So there's our y-intercept. Our slope is rise 3, run 1. You can see it's going to go that way. Go down 3 over 1, down 3 over 1. And we've got an intersection point all the way down at the bottom of our graph, which is right here. And that is negative 2 for the x and negative 7 for the y. So even if they do meet at a perfect intersection point, we still have to make sure we take those extra steps of converting our problems into slope-intercept form. We have to do that like we did for these three equations here. All right, so let's look at a story problem. It says a kicker on the football team, what does that say? I can't see. There we go. Scores 1 point for making an extra point and 3 points for making a field goal. The kicker makes a total of 8 extra points and field goals in a game and scored 12 points. Write and solve a system of linear equations to find the number x of extra points. So x is extra points, and y is number of field goals. So let's, our equations then, we're going to have a total kicks equation. So it says he makes a total of 8 extra points and field goals in the game, okay? So a total of 8 extra points and field goals. So x plus y equals 8. He made a total of 8 of them. And then for our second equation, it's going to be a total points equation. It says he scored 12 points. Right? So it's 1 point for field goal, so 1x, plus 3 points for 1 point for an extra point, 3 points for a field goal, which is y, 3y, and he scored a total of 12 in that game. So now we have our system of linear equations. Okay, so we need to convert both these to slope-intercept form. So this is going to be y equals negative x plus 8. So there's my 8, and my negative x is going to take me down 1 and right 1, so all the way through. Yikes, that is not straight. So all the way through there. And then for my other equation, that would be 3y. We're still going to have to move the x over to the other side, and then we're going to have to divide everything by 3. So y equals negative 1/3. Negative 1 divided by 3 is negative 1/3 x plus 4. So 4 is our y-intercept value there. And then we're going to go down 1, right 3, down 1, right 3. And now we can see where our intersection is right here. So when it says how many extra points and field goals did he made, let's see, x was the extra points. So he made 6 extra points, and he made 2 field goals. So remember, the y-axis was the field goals. You can see he made 2 of them, and the x-axis was the extra points. He made 6 of those. All right, so one type of problem you're going to see on your homework tonight is going to be these break-even problems. So the break-even point of a company is when the cost equals the revenue. So there's some vocab for us. So cost is all the money it costs to have a company. The electric bill, paying your employees, the cost of buying your products before you sell them. Those are all the costs. Okay. The revenue is everything you receive when you sell your services, whether it's products or maybe you're doing a car wash, right? And every car pulls up and you charge them $10, and so you're bringing in $10 a car. That's the revenue. The profit is what you get when it's whatever is left over. So if you take the revenue, all the money you bring in, subtract the cost away, then you get a profit. All right, so if you take the revenue, hopefully the revenue is a lot of money, right? So you bring in the revenue, you subtract away your costs, which you're always going to have. Even if you're doing a car wash, you had to buy soap, you had to buy sponges, you have to maybe pay people to come. Even if it's a fundraiser, you're going to probably have to buy those products. Everything left over is called the profit. So the break-even point is when our profit is 0. Well, why would our profit be 0? Well, our profit, if we're not making any money, that means the revenue and the costs are exactly the same, right? So, So if I bring in $500, but my cost is $500, that gives me a profit of 0. That's not good. So if the revenue equals the costs, then we call that the break-even point. So this says your family starts a bed and breakfast. It spends $500 fixing up a bedroom to rent. The cost of food and utilities is $10 per night. Your family charges $60 per night to rent the bedroom. Find the break-even point. So we have 2 equations here. Let's first do your cost equation. Okay, you're going to have to do these on tonight's homework, so make sure you pay attention for this. The cost equation, it says you spent $500 fixing up the bedroom, right? So it costs you $500, plus it costs you the food and the utilities cost $10 per night. So we'll let X be the number of nights. So you have to pay $10 per night every night somebody stays there. Plus it initially cost you $500 just to fix the place up. So there's your cost equation. Your revenue equation is all the money you're bringing in, and you charge $60 per night. Okay, so the break-even point, when it says find the break-even point, remember we said that's when cost equals revenue. Where are these lines going to intersect? That's what we need to find out. So let's start with the cost equation. The y-intercept is 500, and then we're going up 10. Now, up 10, you can see they're counting by 50s. So if they're counting by 50s, then instead of going up 10 over 1, I'm going to go up 50 over 5. That's going to be the same as a slope of 10, but it'll make this a little easier to graph. So up 50 and over 5 puts me right there. Up 50 and over another 5 puts me right there. So there is my cost equation. You can see it's going up slightly still, and that's because it costs me money to keep the place in operation, $10 a night. But fortunately, I'm bringing in more money than that with the revenue. Now, I don't have a y-intercept here, so that means I'm starting from 0. So it's going to take me a while to catch up. Now, because they're counting by 50s, I don't want to go up 60 over 1, right? So going up 60 over 1 is going to be the same as, if we multiply by 5, going up 300 over 5. Now I can graph this better. So rise 300, run 5. Rise 300 puts us at 600, run 5, and you can see now what our intersection is going to be. So our break-even point is going to be right here at X was 10, right? So 10 nights. Okay, at 10 nights, I will have earned $600 is our Y. And that's our break-even point. So I'm not going to make any money until my 11th time somebody has rented the room. Once somebody rents it for an 11th time, you can see the revenue is now higher than what the cost is, and that's good for us. But that's going to take me 11 nights to do that. So the break-even point, we have our answer, is right here. Okay, if you have any questions, let me know.